Hi, Chemistry 11 students. So with today's lesson and the lesson that I'll do later on today, hopefully, we're going to cover a worksheet which is looking at two topics. One is molarity and the other is dilution. I urge you to look over your notes for this and also do the reading and the other assigned videos. The purpose of this video is to help you with the worksheet that I've just posted up. So some key concepts you need to know. Often in chemistry, you're going to be working with solutions of substances. So very commonly you're working in an aqueous environment, you're working with water, and you're working with something that dissolves in the water. Frequently, you need to know how much is dissolved in that water. What is the chemical amount of a given substance that's in a given volume of water? The topic of that is concentration, but you're going to come to know it as molarity, the moles of a given substance that are in a liter of the solvent. In this case, the solvent is what does dissolving. Well, it's always like that. And in this case, the solvent is water, and it's going to be water for Chemistry 11 and anything I can think of as well in Chemistry 12. So the concepts I'm just going to relate to the worksheet right here. They give an example in the worksheet. Imagine you have a solution. It's made by dissolving 4 grams of salt, I guess just table salt, in 120 milliliters of water. The other solution is made by dissolving 6 grams in 350 milliliters of water. So the question is, which one contains the most salt? Well, obviously that's going to be the one that has the greater mass. Greater chemical amount of salt is in the 6 gram. That being said, which one's going to taste saltiest? Well, if you're putting 6 grams in 350 milliliters, that's less salt per unit volume of your solution. So it's not going to taste as salty. The definition of concentrated, I'd like to see you put that in your own words. Of course, I'm going to be dropping these kinds of concepts throughout this lesson, going through different examples. The opposite of saying that anything is concentrated is saying that it is dilute. You've probably heard that word before, and you'll be hearing it in, I guess, a chemical context for looking at some of the problems today, because we're not just talking about a qualitative statement that a solution is dilute, we're talking about actually attaching numbers to it. How do you take a very concentrated solution with a known concentration and make a solution that has a lesser concentration? This is a problem that we as chemistry teachers often face. In the back chemical cabinet, we have some extremely potent acids and other substances that we would never bring into the classroom. The substances we bring into the classroom, the solutions that we bring into the classroom are much more dilute. What we need to do as chemistry teachers is to figure out the lab calls for this certain concentration of, say, an acid. I have this stock acid, which if I opened up the cap, it would start fuming through the classroom. How do I make something that's a lower concentration that students can work with? This is the concept of dilution that anyone working with chemicals, with solutions, is going to start using. And that's the other concept we're looking at today. There's a lot of equations you need to be looking at. The worksheet has them listed. I'm going to go through a few of them just now that I've written up here. You're welcome to, I'm going to scan through the notes just now on the example questions. Obviously, pause the video if you want. You can go through these. This is the top part of the board. Bottom part of the board, those are equations. And here, questions 3, 7, 9, and then I decided to do 6 are worked up on the board right here. And I'm going to talk through them a little bit later on. The equations that you need to know have units you should be familiar with by now and symbols you might not be familiar with by now. So running through them, concentration. Concentration is how much of a given solute you've got dissolved in a given solvent. This is intimately related with the concept of a solution. The units for concentration are chemical amount per unit volume. You know the unit for chemical amount is the mole. The SI unit for volume is the liter. So concentration, C, is measured in moles per liter. N is the letter we use for chemical amount, moles, and V is what we use for volume. And when you're working with chemicals expressing concentration, you want your volume to be expressed in liters. That's very important. This equation can be rearranged. A way that is often used for rearranging it, that you really need to be familiar with, is this one right here that I'm pointing at, N equals CV. This is a way of calculating the chemical amount you have in a given volume of a solution with a given concentration. You might be conducting some kind of chemical reaction and want to add exactly 0.5 moles of a given reactant to some kind of reaction system. If you do that, you're going to need to know, all right, what is the concentration of the solution that I'm adding, and then how many moles do I need, and then you can figure out what volume you might need. Or let's say you have a concentration in a volume, you want to know how many moles there are. N equals CV. Chemical amount is concentration times volume. For dilution, you got 4 variables. And that might sound kind of intimidating until you realize that to solve any of these kinds of problems that you're going to be looking at, you're going to be given 3 of the 4. You only need to worry about the one that's unknown. There's 4 equations that are really all just restatements of the same concept you're going to see. I'm going to go through those equations later, but the equation that's all based on is this one right here. C1V1 equals C2V2. Well, what does that mean? Well, C1 is the concentration you start with. Let's say I'm making some kind of acid, and I've got this like 18 molar acid that I would never bring into the classroom. That 18 molar or 18 moles per liter stock solution that stays in the chemical cabinet, that's your C1. That's the starting concentration. Your V1 is, all right, this is how much I'm going to take out of that whatever jar or canister. That's your starting volume. C2V2, this is your, C2 is your final concentration. I want to say maybe I want just a 0.1 molar solution, a very weak hydrochloric acid solution. That would be my C2. And then V2 is your final volume. This is based on the fact that when we're doing dilutions, we're not throwing any of the chemical away, or hopefully not dumping any of it anywhere. The chemical amount doesn't change. So remember from that first equation, the one I showed you earlier, N equals CV. The chemical amount, N, equals concentration times volume. So C1V1, well, C1V1 is a chemical amount. C2 times V2 is a chemical amount. The chemical amount doesn't change when you do dilution. All that changes is the volume, and as the volume goes up, the concentration's going down. Just like if you were to take, some coffee and pour a bunch of boiling water into it, and then drink it a little while later, it would taste terrible because it would be dilute. The volume went up, so you got more coffee out of it, but you have a weaker drink. It's more dilute. That's dilution in a nutshell. The chemical amount doesn't change, but the concentration goes down while the volume goes up when you're doing dilution. C1V1 is the chemical amount you start with. C2V2 is the chemical amount you start with. They are equal, but we can use situations with dilution where, let's say we know C1, we know V1, and we know C2. What's the final volume? Maybe we have that 18 molar, that stock acid solution, and we know we have an initial volume of, say, 18 milliliters, or I don't know, 10 milliliters of that, a very small amount. And we want a final concentration of 0.1 milliliters, 0.1 moles per liter. What is our volume going to be that amount of acid will be dissolved in? That would be your V2. It's going to be higher. You bring up the V2 by adding water. The water is not acid. The water is not your hydrochloric acid. It's just what the acid is in. So that's the concept of dilution. 4 variables. You'll be given 3 at a time. You need to solve for the 4th one. Looking at some of these example problems, example calculations. Having gone through some of these equations, I'm going to also remind you of some stuff. Molar mass is something you should know how to calculate, and you need to use it for some of these problems that I've made up. Question 3 is this. A solution is made by dissolving 24 grams of NaCl, sodium chloride, to make 475 milliliters of solution. Calculate the concentration in units of molarity. Hey, so they give us steps here. This is a useful thing. The first thing we need to do is to figure out how many moles have we got. All that we've been told is the amount is the mass. We can find this out fairly easily. What we need is the molar mass of sodium chloride. Your reference should be the periodic table in your textbook, the paperback book. Using that as a reference, I find this. The molar mass of sodium, 23 grams. The molar mass of chlorine, 35.5 grams. There's one of each of them, NaCl, one of each of those ions. The 23 and the 58 and the 35.5 add up to 58.5. In other words, every mole of sodium chloride is 58.5 grams in mass. How many moles is 24 grams? Your moles is equal to your mass divided by their molar mass. There's an equation you're going to see, I think, pretty frequently. Moles is mass divided by molar mass. Grams divided by grams per mole. You've seen that before. Now, what is it? In this case, when I do that calculation, 24 divided by 58.5, I get 0.41 moles. Done. That was step 1. Step 2, well, we need to go to liters. It's important to do that. Often you're going to be given values in milliliters, or maybe you'll want to express it in milliliters at the end. When you're doing your calculations with molarity, it's got to be in liters. So, we're told it's 475 milliliters solution. It's easy to make the conversion. If we want volume in liters, we take volume in milliliters and divide by 1,000. I made an equation for it. VL equals VML divided by 1,000. Well, 475 divided by 1,000 is 0.475. That is to say, 0.475 liters. That's question answer for 3B. And C, now we take those 2 pieces of information and we combine them. We have the concentration. Our formula we need to use is C equals N over V, the one I described over there. It's 0.41 moles of sodium chloride divided by 0.475 liters. Notice how I put the sodium chloride as part of the units here. Now here is our solution. 0.86 molar. I guess I really should put 0.86 molar sodium chloride to be consistent. I have 0.86 capital M, big M. That is that's the symbol we use for the unit called molarity. You can also express this as moles per liter. Either is correct. It's just easier to write a capital M, and that's what chemists do. What I actually did is I decided I would do question 6 as well. I'm going to do that one instead next. So question 6 is this. This is on the 3rd page of your assignment. Bear with me for a moment. Here. Consider 670 milliliters of a 4.10 molar solution of magnesium nitrate in a beaker. If you evaporate all 670 milliliters of solution, how many grams of solute will be left in the beaker? So, what you need for this is you need the mass. You need the mass of magnesium nitrate. that's present. How do we get there? We need to get it by getting two things. We need to get the chemical amount and we need the molar mass. All of that is available to us. I start by calculating the molar mass. Here's where you want to do a bit, well, you want to be careful. It's easy to go to the periodic table and find the molar masses of the elements. The only possibly tricky bit is making sure you use the subscripts correctly. The formula for magnesium nitrate is Mg, and then brackets, NO3, and then a 2 at the bottom. That's 2 nitrates. Each of the nitrates has 1 nitrogen atom and 3 oxygen atoms bonded together to form an ion. So the total molar mass is 24.3 grams per mole. That's the magnesium, plus 2 times 14 grams per mole. That's from your nitrogen, plus 6 times 16 grams per mole. That's the molar mass of oxygen multiplied by 6. 3 times 2 is 6. When I add those up, I get 148.3 grams per mole. In reality, you can just look up molar masses on the internet. I won't know the difference, but you should know how to calculate them. Your chemical amount is the concentration times the volume. This we are also given. N is molar is the molarity. N equals the molarity times the concentration. So in other words, 4.10 molar times 0.67 liters. Notice I took that 0.67 down to 2 significant figures. I'm making the assumption that that last 0 is not a significant figure. I have 2.8 mole written here. Notice I also wrote down do not round yet. Your calculator will say 2.75 molar. You don't get that third significant digit when you do the final calculation, but don't take it out yet, otherwise you can make a rounding error. The mass is the chemical amount times the molar mass. That's just a rearrangement of the formula I showed you earlier, and it's another one you should know if you're asking questions like, how much of this chemical do I need to make this solution? Or, to weigh this, whatever. How much of this chemical do I need if I have a given number of moles and a molar mass given? Mass is 2.8 moles times 148.3 grams per mole. I get 410 grams. If you were saying, oh, actually it's 3 significant figures, then you'd be saying 408 grams with 3 significant figures. But I just put down 2. Question 7 is shorter. Question 7, we just need chemical amount. Chemical amount is concentration times volume. N equals CV. C equals 2.5 M. That's moles per liter. V equals 1.5 liters. N equals 2.5 molar times 1.5 liters is 3.8 molar. Again, I'm rounding that, so I am just keeping 2 significant figures. Question 9 has a bit more detail to it. For question 9, let's go to it. What is the molarity of a 500 milliliter solution containing 249 grams of Ki? Ki is potassium iodide. 1 potassium atom, or 1 potassium ion, which will have the same mass, and 1 iodide ion. The molar mass, well, let's see now. We can get in this fashion. 39.1 grams per mole is from the potassium. 126.9 grams per mole is your iodide. We have a total of 166 grams per mole as the molar mass of potassium iodide. The number of moles of it, mass divided by molar mass, 249 grams divided by 166 grams per mole. It's a very clean calculation. It's 1.5 moles. Now we can find concentration. We have chemical amount and we have volume. C equals N over V. 1.5 moles divided by 0.5 liters is 3 molar. Notice I'm just using 1 sig fig here. If in reality I had a highly precise device for measuring the concentration, or measuring volume, I could say 3.00 molar. Here I'm going by the conventions which are allowing for 1 sig fig. Those are the questions on molarity that I wanted to review. The next thing I'm going to do is I'm going to review 3 questions about dilution, and then I'm going to see about getting that lab in play. That's dilution formula can be rearranged in the following way. C1 equals C2 V2 over V1. In other words, my initial concentration will equal the final concentration times the final volume divided by the initial volume. V1 equals C2 V2 over C1. This would be when you're asking questions like, how much of this do I need to start with if I have this final volume, this final concentration, and this starting concentration? How much stock solution do I need, for example, for a certain chemical reaction? C2 equals C1 V1 over V2. This is end concentration. This will be your diluted concentration, the lower of the 2 concentrations, the diluted one. And then V2 equals C1 V1 over C2. That is just 4 ways of saying the exact same thing. You will use different arrangements of that formula for solving different problems. I'm going to show you the 3 questions that I did, and you can pause the video if you want. So there's the first one, the second one, and the third one. I'm going to walk you through what we have. There. Question 11, we needed the starting volume. What volume of 3 molar HCl is required to make up 5 liters of 0.25 molar HCl? So we're starting with a stock solution of 3 molar hydrochloric acid. How much of it do we need to make up 5 liters of a 0.250 molar hydrochloric acid? V1. So the formula that we needed to use there was V1 equals C2 V2 over C1, just like you saw it written up on the board over there like I did. I then took the formula and I plugged everything through. Really straightforward. 0.250 molar times 5 liter divided by 3 molar. I get 0.417. Now, of course, your calculator won't tell you the units. The units are liters. You will often then want to say, well, my glassware gives me volume units of milliliters. So you're going to run with that. What are the units in milliliters? How do we express it in milliliters? Well, it's 417 milliliters. That's just multiplying that value by 1,000. The next question I reviewed was 13. In that case, we needed C2, final concentration. The question is, what concentration of sodium chloride solution is made by diluting 3 liters of 0.850 molar NaCl to 12.5 liters. C2 equals C1 V1 over V2. C2 equals 0.850 molar times 3 liters divided by 12.5 liters, and I get 0.204 molar. That's the final concentration, the diluted concentration. The third question, 15, we needed C1. Where's 15? If 65.5 milliliters of HCl stock solution is used to make 450 milliliters of a 0.675 molar HCl solution, what is the molarity of the stock solution? The only issue that makes this one the tiniest bit harder is that in both cases we've got units is being expressed in milliliters, and we also have to worry a bit about sig figs. We're only going to have, I would say, 2 in the final answer. Otherwise, C1 equals C1 equals C2 V2 over V1. When you plug that through, just like you saw on the board, the answer, correctly rounded, is 4.6 molar. So that's the use of these equations. I think you'll probably find that it's not too difficult to get there. I thought there's one other thing I might like to show you for today. It makes things a little more interesting if you actually show what things look like. I looked at question, I believe it is 5. Now let me be sure about that. No, question 4a. They ask you to calculate the concentration in units of molarity for the following solutions. And it is 42.1 grams of calcium nitrate in 700 milliliters of solution. Now, I don't want to waste 42.1 grams of calcium nitrate. So I thought I would just divide this whole thing into by 10 using my scale. This is calcium nitrate. Notice the equation formula for it right here, and notice that often on chemicals they will give you the molar mass. That FW is actually the same thing as molar mass. So let's see. I'm not going to use 42.1 grams. I'm just going to use 4.21 grams, and I'm going to dissolve it in. What do you think? 70 milliliters. I'm dividing everything by 10. So I have a beaker. I put it on the scale. I don't want to spill a strong oxidizer all over the place. If you ever work with nitrate salts, one thing you'll find about them is, well, for one thing, they're very strong oxidizers. They're not things that you would ever want to be exposed to on your skin. The other thing is that nitrate salts are extremely soluble. You can make a nitrate salt by taking the associated metal and reacting it with nitric acid. Nitric acid is an extremely potent acid. The school has it, but we never use it because it's such nasty stuff. .23 grams. 4.20 grams, back to 4.23. These are large crystals. It's difficult to measure this. This might be it. 4.21 grams. So here's our 4.21 grams of calcium nitrate. And off the scale. And I want that to be in 70 milliliters. I'm going to put this is the calcium nitrate right here. Looks just like table salt, but it's not. This is going to be dissolved in 70 milliliters. I'm going to measure out my volume. I'm going to add the, actually, you know what? No. I'm going to add the calcium nitrate to the cylinder. One thing you find is that when you add a solute to a solvent, often the volume changes very little. The solute is able to kind of stack into the solvent in a way that the volume doesn't increase very much, not at least until you add a very great amount of the solute. So I'm going to bring this up to 70 milliliters. Right now the meniscus has it at about 68. Now, There. You don't want to store your calcium nitrate in the cylinder at all. Once I'm done with this, I'm going to pour it out. In fact, I'm going to wash it out once I'm done. You can see already that the nitrate salt is very nearly done dissolving. As I say, nitrate salts are extremely soluble. Metals that would otherwise not be dissolved in a given solution will dissolve just fine in nitrate as a nitrate salt. So I've probably left a little bit behind. I'm going to go back. Just for the record, there's better equipment for doing this. If I wanted to be much more accurate, I would be using a burette, and I would also be using a volumetric flask, which I'm going to show you in a moment. You're probably aware that the triangular profile flask is called an Erlenmeyer flask. Erlenmeyer flasks are good for storing chemicals because they have a narrow neck, which means they don't have evaporation quite so easily. And they also don't tip over very easily. This is a beauty of an Erlenmeyer flask. The cost you pay with an Erlenmeyer flask is they're no good for measuring volume. It will only give you very vague measures of volume. But this is good enough. I can see with this that I've been successful at creating 70 milliliters of this calcium nitrate solution. As per the answer for question 4, I've made a solution that's 0.3, well, how many sig figs? The answer for question 3, or 4A, I get as 0.4 molar. If you had more sig figs, I would say here I had at least 2 sig figs. The measurement of volume maybe isn't down to 3 sig figs. I would assess this as most likely around a 0.37 molar calcium nitrate solution. So that's preparing a solution. I had a given mass and I had a given volume. From that, I was able to calculate the molarity, the molar concentration, expressed as capital M, 0.4 M if you only have 1 sig fig, or here I think I've got certainly 2 significant digits, 0.37 molar calcium nitrate. There. That is the first example I wanted to show you. Second example I wanted to show you is a dilution. So I went into the back chemical cabinet. I found this right here. This is iron nitrate. It's a very nice color. Again, notice your nitrate salts won't have a lot of sediment at the bottom right here. Nitrate anion leads to salts that are extremely soluble, not like, say, iron sulfide, iron oxide, where it would sink to the bottom. So a very soluble compound, 0.2 molar. So this solution is really only down to 1 sig fig. But let's say this is too concentrated for what I want to do with it. Let's say I want a 0.02 molar solution. I want a solution that is 10 times more dilute. Well, what will be a way to do that? In this case, I'm going to work with 2 pieces of equipment that you're going to see later. I'm going to work with a 10 milliliter graduated cylinder, which will give you 2 sig figs, actually 3 sig figs of volume, and a 100 milliliter volumetric flask. Volumetric flasks are pretty awesome because they give you an extremely accurate measure of volume. Where they drop off a bit is that they only give you one. They'll tell you the exact volume, as long as the exact volume you want is a certain set volume. Like in this case, 100 milliliters. There's no graduated lines on this. It will only tell you one piece of information. Are you at 100 milliliters? Yes. You will know it if the meniscus is at the line by my fingertip. There are volumetric flasks for 100 milliliters, I think 50 milliliters, 250, 500. I've seen them going down to a liter or going up to a liter. Bottom line is they give you very accurate measurements of one single set volume. So I'm going to take 10 milliliters and I'm going to dissolve it tenfold. You might think, okay, well, I guess he's going to add 100 milliliters of water to it. No, I'm not. I'm going to just dilute it tenfold, which means that it's going to be an environment that's 1/10 the level of concentration. What I'm saying is I'm going to combine it with 90 milliliters of water. If you do the maths on that, how about we do that? So I want C2 to be equal 0.02 molar. All right? Here's what I've got. I want to calculate how much do I need of the V2. Well, let's see. V2 equals C1 V1 over over C2. Okay, so our V2 equals 0.2 molar times our V1, which is 0.01 liter, divided by our C2, which is 0.02 molar. That's our desired concentration. If you do the maths on this, you're going to find that you're going to get V2 equals 0.1 liter. In other words, 100 milliliters. It's going to go into 100 milliliters. We need to add 10 milliliters and top it up to 100. That's how we'll get our solution. We need to add 90 and not 100 milliliters to this. So let's go and do it. Should I be using a funnel? Yes. Not bad. That's 10 milliliters of the 0.2 molar iron to nitrate. Let's just check. The bottom of the meniscus is at the 10 milliliter mark. If it was above the 10 milliliter mark, I would need then to use a dropper, a pipette, to take some out. If it was below it, I would take a pipette and put in 1 or 2 drops to get to that exact level. I want the bottom of the meniscus to be level with that white line at the top. And that's how I know I've got 10 milliliters in this graduated cylinder. I've reached that top line and no higher. So now what I'm going to do is I'm going to, this time I'll use the funnel. I'm rinsing the funnel in case there's any contamination on it. If a bit of extra water gets in there, it doesn't matter because I'm going to add a bunch. Now you might ask yourself, isn't there some water left? Isn't there some solution left behind in here? And you would be correct. Yes, there is. So I'm going to rinse it out. Not once, but 3 times. And now is when I need to be especially careful because I don't want to overshoot. It's pretty difficult to take out water once it's not water anymore, once it's become part of the solution. If I were to do that, to take out some water, to overshoot and take out some water, I'd be taking out solution. I would actually be reducing the chemical amount, and my concentration would be off. So here's where I need to be very slow and to pay attention to the line. It just happens that the line is almost exactly lined up with the bottom of the funnel. Nonetheless, I have to pour carefully. When you're working with a volumetric flask, you find that the very top bit, it shoots up really quickly. Oh, that's annoying. At this point, I'm done with the funnel. I don't want to mess up. I haven't reached the line yet. I have a bit of water left in here. And there. If you look, you will see it does actually the parallax of the camera makes it look like it didn't work out at all, but I can assure you that if I keep the meniscus level to my eye, that the bottom of the meniscus actually does line up perfectly with that line, which is what I want. Now, of course, there's a lot of water up here relative to down here, but you don't have to store your solution in this volumetric flask. It's not necessary. You can now transfer it to a storage container. So, whatever. Let's pretend this is a dry beaker. Swirling this around, making sure I don't leave a bunch of concentrated solution at the bottom. And there. This is tenfold diluted. Do note, it's much paler in color than the original stock solution. Why wouldn't it be? It's more dilute. That's molarity and dilution. I hope you found that useful. What I'm going to do at the earliest convenience is I'm going to put up a video as well on the dilution lab itself.